All right, our next speaker is Marina's minor research. And it's Clément Bonnerot, who's going to tell us how the first light from tidal disruption events.
Yeah, so yeah, like Martin said, I'll talk about tidal disruption events, and in particular, recent progress we've done in the understanding of the hydrodynamics of these events, and in particular how the gas drip from the star ends up forming an accretion disk. And this is an important step because, as you well know from this accretion disk, then one can eventually detect these events electromagnetically. So if that's okay with the chair, I'd like to allow questions during the talk, because I think it's better this way. So feel free to interrupt me at any time if there's anything unclear. I think it's okay if it lasts longer than. And yeah, this is work done in collaboration with Wanmin Liu, now at Berkeley, Martin Pesach here in Copenhagen, and also Phil Hopkins at Galactic. All right, so small delay from the Zoom. Yeah, I'd just like to start by reminding ourselves of perhaps one of the main interests of TDEs in somewhat of a schematic way. So this is showing the black hole mass function. As function, so supermassive black hole mass function, and this is the observations that can be made with other methods, such as using the high luminosity of quasars at high black hole masses, and also direct dynamical measurements around these black hole masses. But these measurements become increasingly unreliable at lower black hole masses. Unfortunately, this is where TDEs are supposed to be good in principle at measuring the black hole mass of the black hole mass for this event. And this is also, so yeah, there's an upper limit, as you well know, which is given by the radius, the black hole above which the star would get inside the black hole before being disrupted, and the lower limit here is less stringent, mostly given by whether or not such black holes at low mass exist. And this range of supermassive black hole mass is also important because it allows us to probe the origin of supermassive black holes, and there are, as far as I know, two main mechanisms. The first being the formation from primordial stars in the early universe. And when you use these seed black holes and evolve them towards, up until our current time, the prediction is that they would lead to a high occupation fraction, namely that most galaxies will host a black hole, including the lowest galaxies. And in this plot, it will show up like a line that keeps increasing at lower supermassive black holes. And another competing mechanism is the formation from direct collapse black holes. So instead of stars, the black holes in the early universe still are formed from the collapse of very massive clouds of gas. And again, if you evolve these seeds to the current time, now still there are some black holes in the highest mass galaxies, but the lowest mass galaxies don't host black holes. So this is a low occupation fraction, and it will show up instead in this plot schematically as a curve that keeps decreasing at lower and lower black hole masses. So this is really the location where we see kind of deviations between these two theories. So TDEs really can help us put constraints on these two, on which combination maybe of these two mechanisms are actually the dominant one. All right, so yeah, that's the main takeaway. And also, as you probably well know, the future is very bright for TDEs. This is showing the number of TDEs per year of discovery. First TDEs were detected in the 90s, smoothly increasing, in particular thanks to the Zwicky Transit Facility, up to now about maybe 100 TDE candidates. And in the future, we're here. And in the future, thanks to the Rubin Observatory, this sample will increase by 1 or 2 orders of magnitude. So very promising time, and the Rubin Observatory should be starting operating next year. All right, so perhaps this slide was not necessary after yesterday, but just to remind ourselves of the main observational properties of TDEs that models should for sure be able to explain. These are showing different light curves from TDEs, and you can see there are month-long luminosities in between 10 to 43 and 10 to 44 arc per second. And those emissions are multi-wavelength, but in this talk, I'll focus mostly on the X-ray and optical. And as was mentioned many times already, some TDEs show only X-ray, some only optical, some both at the same time, like this one. So models should be also able to explain this kind of variety in the emission properties. So yeah, as theorists, the goal here is to basically build a robust model that can be first used to account for these properties, and also in the future be used to extract the system parameters such as black hole mass from the many TDEs that will be discovered in the near future. All right, so you probably at least seen one version of this schematics in the last few years, but I'll show it again. So this is showing basically the hydrodynamics of tidal deception events according to our recent understanding of it. So it starts from a star that is plunging towards the black hole on a parabolic orbit, entering the tidal radius, and as a result, the star gets disrupted and its debris gets scattered on a wide range of trajectories, roughly half of them getting unbound from the black hole and the rest getting bound on highly eccentric orbits coming back towards the black hole. And here there are two important properties that should be kept in mind about this stream is that the width typically does not exceed tens of stellar radii, and this is physically because of the confining effect of self-gravity that is still important in this direction. And another property relates to this fallback rate that we heard of already several times. It will typically rise on a timescale t-min that is roughly a month, and then at later times decrease with a characteristic decay law of time t to the minus 5/3 power. So until that point in time, the hydrodynamics of TDEs is robustly understood, has been predicted back in the late 80s and confirmed by many works. But unfortunately, there's likely no observable signatures until that point in time, and most of them instead will come from later on when the streams will form an accretion disk, and this phase is much less robustly understood. So the main reason why it's not understood is because of a computational reason that essentially prevents from reaching a high enough resolution in simulations. That's if they are global and 3D, especially near the black hole. And the reason is that if you have a high enough resolution in the star, because the star is stretched by orders of magnitude in the radial direction, then the resolution, especially at per center, becomes much lower, and actually current computational capabilities may not be enough to run such a global 3D simulation. So our strategy was to instead focus on the different phases that were identified as the most important in this evolution, study them with resolved local simulation, and then put the different pieces together to get an understanding of the global evolution. So the evolution algebra is based on this method. All right, so what happens is that the stream comes back at per center, that is typically tens of times the gravitational radius of the black hole. As a result, the stream precesses. Another thing that happens at per center is the nova shock that's caused by a strong compression of the stream at that location. Because of precession, the two parts of the stream here will be on a collision course, and if everything was to happen on the same plane, these two streams will collide. But if the black hole has a spin that is not orthogonal to the angular momentum of the that is not aligned with the angular momentum of the gas, then another effect, length slowing precession, would actually make this part of the stream on the different plane from that part of the stream. And in that case, the collision may be prevented, and several revolutions will be needed until eventually a collision does occur. Here. And once this collision has happened, it leads to a shock, self-crossing shock, that dissipates a fraction of the stream's kinetic energy, converts it into radiation that makes this gas expand quasi-spherically. At later times, this gas keeps expanding, but its trajectories are affected by the black hole's gravitational force. And so they get curved, and then more collisions are expected on that side of the black hole, which lead to what we call the secondary shocks. These shocks may be radiative in the extreme UV band, but most importantly, they are strong enough, we find, to form an accretion disk around the black hole. And once an accretion disk has formed, accretion proceeds, and this is likely to lead to X-ray emission. And in this picture, the additional optical emission is due to reprocessing. Essentially, the high energy photons have to diffuse out of this opticalistic envelope, and by doing that, they get absorbed and re-emitted several times until when they emerge, their frequency has shifted and they are now optical photons.
Sorry, just to clarify, the secondary shocks come from the CIO hitting the.
Yeah, basically the CIO, also this outflowing gas from the self-crossing shock.
Yeah.
it expands
Yeah.
until it reaches the black hole, and because the trajectories that of the gas that gets close to the black hole are curved, this leads to collisions around here.
Okay, so, it's most of the energy from shocks from the outflow hitting like the debris streams, or is it just with itself?
All right, so this, roughly speaking, the strength of the collision would be given by how far from the black hole they happen.
Right.
So this collision would be less strong than the ones happening closer in. Yeah.
Okay.
The reason why it depends on the distance from the black hole is simply that the velocities there are. Is there any other questions?
What is the time delay between nozzle shock happening and secondary or shocks? I mean, does nozzle shock predict some precursor of the?
No, most likely you will not predict some precursors. I mean, I think there's some work that predict a precursor, but the reason why I think there shouldn't be a precursor is that even though there's heating at the nozzle shock, first of all, the heating rate is something around, I think, 10 to the 40 arc per second.
Mm-hmm.
I think, and also the gas is so optically thick that only a fraction of this heating rate will actually make it out as a observable luminosity. So I think it's very unlikely that it will be detectable.
Is there a shock breakout at the nozzle shock? Namely, you compress, you have a shock of some strength, does something then go back out and actually have a breakout of the stream?
Yeah, I've not thought about this, but I think that's a possibility. I think in that case, the luminosity may be larger than.
Yeah, that was the thinking.
I mean, I know that has been thought about for like initial passage. I thought we were going off for nozzle shock.
You mean from the first disruption, right?
Yeah, exactly.
Oh, it is from
Yeah.
the first room. Okay, I was thinking of it.
But the effect is the same. Interestingly,
Yeah. Yeah.
both effects are due to the fact that close to the black hole for high beta, if you're talking about the disruption, the tidal force dominates, and so the star or stream are confined into two planes, and so this leads to a strong compression. The difference is that for the disruption, you have much more mass, so you expect to have strong shock breakout.
Yeah.
So, maybe if I think a difference between the star and the stream, though, is that the nodal shock is happening continuously.
Mm-hmm.
So maybe the time scale, probably actually the time scale will be longer, but the luminosity may be smaller. I don't know actually how high the luminosity would be. It would be worth looking into.
Is there a way you can form an elliptical disk, a highly elliptical disk, or is it just, does it become like a spherical photosphere?
Yeah, so in the case, I will show simulation of this later, but in the case we simulated, the disk is rather circular, eccentricity maybe 0.2 or something. And interestingly, something that I will not show is that we also find that this is rather independent on where the self-crossing shock happens actually. So you may expect, that if the crossing was to happen further out, maybe the disk would be more eccentric. But what we find is that as long as this crossing happens and efficiently leads to an outflow, then the formation of the disk from this outflow will lead to a disk that is still roughly circular. All right, so yeah, in the rest of the talk, I'll basically come back to these different phases, starting from the nodal shock, and then the self-crossing shock, understanding the properties of the outflow launch from the collision point. And then, so those two will be studied with local simulations, and then I'll go to the global frame to understand what is the later evolution of this outflowing gas, in particular how it forms an accretion. Right, so starting from the nodal shock, so that's the stream coming back, reaching percenter, and because the tidal force dominates in this region, if you were to look along this direction, you would see a stream that looks like that, and the upper part and the lower part would follow different orbital planes that cross near percenter, and therefore the stream gets confined to a very small width that leads to an increase in pressure, actually a shock, and this causes a bounce of this gas as it moves away from the black hole. So this interaction is extremely difficult to study numerically because of the extremely high resolution you need both in the stream, but also, especially at Earth center, because the stream gets confined to an extremely small width, a small fraction of the stellar radius. So instead of trying to push the limits of what's computationally feasible, what we did is to use 2D simulations that evolves a section of stream. So starting from this section, this is showing density that is inside this red rectangle, and evolving this section of gas around the black hole through the null shock and back in the blue point to understand, is whether there's an effect of this collision on the hydrodynamics of the stream. So yeah, initially you'll see that the streams get squeezed because of the tidal forces, and I'll also mark the outer boundary of that stream for later comparison. So here the stream gets compressed as it's approaching the black hole, and when it reaches Earth center, the nodal shock happens. There's a bounce after the pressure has built up, and then the stream is moving away from the black hole, expanding again. But the main takeaway here is that even when the stream now has reached this blue rectangle, still most of its mass is still confined inside the original boundary, which it has in the red rectangle. So the main takeaway here is that there's no significant net expansion from the nodal shock, such that this picture of two thin stream components is actually the picture that I would expect physically. I have to emphasize that this result is not recovered by global 3D simulations. So I think this is an important, the reason for these differences would be very important to understand. Maybe that's a good topic of discussions for this afternoon.
And this is adiabatic.
Yes. But this is also well motivated by the high optical depth of the right. So
can you please mention what's the sort of resolution you will need to recover this kind of more accurate nozzle shock calculation? Roughly.
I would say at least 10 resolution elements in this direction, but that may not be enough. And also you have to remember that this has to be, in the Lagrangian method like this one, if you have 10 resolution elements at a given time, you will still have 10 resolution elements when the stream has been confined to a very small width. But with grid-based code, you may need to have an extremely large number of cells if you want to resolve both, the stream when it's thick and the stream when it has reached its maximal compression. So yeah, 10 resolution element at least, but at every single time.
Have you done this at 100 times lower resolution to see if you get artificial expansion?
Yeah, I did, and I don't get artificial expansion. No.
So this is like a 2D cut through the cross section, and like a 2D cut through the stream. So we're looking at a cross section. Would you imagine if there's any like longitudinal stretch? Because here we are confining every compression inside this like 2D plane. So would you think if we have any longitudinal effect, would that change anything?
Yes, so that's a good point. And basically, if I understand correctly, what you're referring to is the fact that, if you were to start from two fluid elements that are very close to each other, but slightly different location along the stream, and as these two fluid elements evolve, they will actually get further and further from each other. Right? In other words, the mass between these two is constant, so you should have a lower density due to that effect. Turns out this is actually included in this simulation because you can actually predict this effect by just imposing an evolution of the density on top of the compression. So the decrease in density due to that effect is included, but it's dominated by, so that would lead to a decrease in density, but this decrease is dominated by the increase in density due to transverse compression. Does that make sense?
Is this in GR or in Newtonian gravity?
Newtonian gravity.
I mean, you could, obviously doing things in full GR is obviously a tremendous amount of work, but if you used just like the relativistic tidal tensor and things, I think in general, if you had an inclined, if you had a spinning black hole in an inclined orbit, the directions on which the tidal forces are, you're getting squeezed in two directions and stretched in the other. If those a rapidly changing direction as you have kind of apsidal and nodal precession near pericenter, that kind of twisting of the tidal forces could spread things out maybe.
Yeah, I think that's a very good point. Basically, something to keep in mind is that the kinetic energy in the transverse direction or the vertical direction is much smaller than the orbital kinetic energy. So if you transfer even a tiny fraction of this orbital kinetic energy into vertical expansion, that can change the result dramatically. And this may be.
I mean, I was actually advocating doing this back in Kyoto, that you could, if you did your Newtonian self-gravity for your stream, and especially in your confined little box, same kind of box style simulation, but then looked at a Kerr geodesic and just artificially put in, if you knew the tidal temperature as a function of time along the stream and just put that in as, and see what happened to your gas, I think that'd be very.
Yeah, you don't even need self-gravity actually. Gas is.
Yeah, I mean, it would not be hard to just take some Kerr geodesic, find the tidal tensor along it, and then impose those tidal forces on your box. That would not be hard to do.
We can talk more. All right, so the next step is to understand what happens to the crossing between these two streams. And I think I'll go pretty quickly on this. Basically, we did this simulation in the co-moving frame that moves at the common tangential speed of the two streams here. In that frame, the two streams are colliding head-on with a velocity equal to the radial velocity in that frame. The orange arrows here, and what we find is that this kinetic energy gets dissipated. As a result, the stream expands, and because this simulation is adiabatic, the terminal speed of this outflow is equal to the radial velocity. And if you boost this picture back in the lab frame, the result is that the stream is still expanding spherically with a velocity VR in blue, but now there's a tangential net speed towards the left. And this implies that there's always a cone of and bound gas moving towards the left, and some gas moving on retrograde orbits compared to that of the stream moving towards the right here. But besides these detailed velocity profiles, the main takeaway is that the outflow expands quasi-spherically and it's launched from the collision point.
When you say unbound, you mean unbound to the black hole?
Yes. Yeah, the reason is that the stream is on a very marginally bound orbit, 0.99 for the eccentricity. So the additional acceleration given by the expansion is actually able to give it a kick that's small, but enough to make it unbound.
You're heating it up and then the pressure is pushing you.
Yes.
I have a quick question. The other day we heard that a possible explanation for the radio emission observed is originally bound part of the stream. Would this contribute significantly?
Definitely. Yeah, we in the paper we make estimate for the radio emission could be coming from the.
So can it also have an X-ray? Like, can outflow be in the X-rays?
Yeah, that's a good question. I would personally not expect to have X-ray emission, but that's something to be.
You mean if it hits something or like what?
Well, you mean from this collision?
From it is.
Oh, I thought you said from, okay. Why would
you? I think it's, yes.
How
That's something
fast
that-
are these outflows?
It's 3% of the speed of light, typically.
Okay, so it's pretty slow compared to like the X-ray ultra fast outflows.
Yes.
And how much mass comes out?
So that depends on the parameters, but at most you can get half of this sphere would be unbound, and because only half of the star comes back, it would be a fourth of the star. If you were to assume that this outflow was steadily fed from streams. So, but that depends on the parameter, depends on how strong this collision is. How much time do you have?
It's 10:12 now.
I have until.
Until 10:30.
Oh. Yeah, something that I think is worth mentioning is what kind of luminosity, volumetric luminosity you can expect from this collision. Because this collision has been proposed as the origin of the optical emission. And in the context where these two streams are very thin, the takeaway is that I don't think that you can expect the luminosity from this collision to be explaining the overall luminosities. And the reason is that the upper limit on the luminosity you can get is given by the heating rate, so the infrared times the specific dissipated kinetic energy. And if you inject typical values, this heating rate is typically less than about 10 to 44 arc per second. However, because the photons are created on such small scales, the scales of the streams, but because of the high optical depth of this outflow, they actually have to diffuse up to a very large trapping radius before emerging. Essentially, what it means is that the photons lose energy by doing work on the gas until they reach this very high trapping radius. So because this trapping radius is so high, only typically 5% of this heating rate is actually emerging as luminosity. So when you combine these two equations, typically the shock luminosity would be of the order of 10 to 42 arc per second. But I want to emphasize that this depends on parameters, and there may be some preferable region of parameter space where this could lead to potentially a larger luminosity and maybe also a precursor for TDEs. And I can refer you to the work of Shoshan, who did some more detailed work on that. All right.
Do you have a sense of how, I mean, optically selected would by definition select the events for which this is as large as possible? So what fraction of tidal disruptions might it be, you know, larger than your typical estimate? What is this? This just depends on the pericenter radius and the spin of the black hole and exactly where the self-intersection shocks are.
So I don't think it would strongly depend on the spin of the black hole, but it would definitely depend on the mass of the black hole, because it will give you higher black hole masses would give you stronger shocks.
Yeah.
But on the other hand, so it basically increase this dissipated energy, but the high mass black hole will also decrease the fall back rate. So this kind of go in opposite directions. But I think that in that case, still you can expect maybe an emerging luminosity that is 10 to 43 or maybe a few times that. So that's an interesting one. Right. Another thing I wanted to touch on is the possibility that these collisions are offset, and this is expected if the black hole has a spin. In that case, you know, these two stream components are not on the same plane; they have some vertical offset delta z. That is, if you were to loop along this direction, you would see two streams that are offset with that delta z, and if delta z is 0, that's the normal non-spinning case. If delta z is larger than h, there's no collision at this specific passage. But if delta z is in between 0 and h, then you expect to have collisions that are offset. And this is work that has been done by PhD student Tai Yankovic. In this paper that is now on the archive, what he did is basically local simulations of this offset collision. Actually, in that case, the collision is not offset, but the setup is basically injecting gas towards two streams towards each other from this orange segment. So in that case, there's no offset, so the outflow is roughly symmetrical with respect to the equatorial plane. But if the collision is slightly more offset, delta z, not 0, but still small compared to h, the outflow is slightly less symmetrical. And in a more extreme case, where delta z is a significant fraction of h, in that case, the outflows are really qualitatively different. They are actually collimated in the direction of the original stream. So there are other consequences of these offset collisions, in particular for the reprocessing efficiency of the outflow. You know, you may expect less reprocessing if the outflow covers less of the solid angle, and the exact predictions, you can find them in this paper. The main takeaway here is that this offset can lead to deviations from sphericity.
Could it also maybe lead to higher rate of efficiency if you could, stuff could get out of the, you know, in certain directions? But
Oh, you mean like photons getting out from there?
Yeah.
Yeah, it turns out I'm not so optimistic that this could take place actually, because you know, if the outflow is collimated, okay, maybe the kind of the outer radius in some specific direction is lower, but also there's more mass. So I think that actually these two effects may compensate, and the trapping radius may be actually the same in these two cases. So, but that's something that we also investigated. Yeah.
Maybe I asked similar question, but so the deviation from sphere you predict. So is it? Can you Can you explain the observed polarization from optical TDEs? I mean, several TDEs show very high polarization degree. So
Yeah, I agree that from these polarization measurements, you expect the spherical photosphere, so it would be hard to account for if the sphere is not spherical. So maybe that is something that happens at early times, but quickly after this, the envelope will become more and more spherical because of interactions between these two outflows. It's also possible.
So gradually polarization decrease.
Yes.
Are there any predictions for like differences in outflow velocities from here? It's not obvious to me necessarily that there would be. Although.
Yeah. The outflow velocity is always given by the velocity of the collision. So there's no change actually in these different cases. All right, and that's the final part of the talk. Here I will show the later phase of evolution when the accretion disk forms. And that's basically done by doing a simulation that starts from the outflow from the side passing shock, so the stream processed, collected here, and the colored gas here is showing the density of the outflow. In that case, there's some unbound gas moving towards the left, roughly 30%, and also retrograde gas. So the evolution is like this. The orbit gets curved due to the black hole's gravitational force, and this leads to collision around the black hole that can form an accretion disk. So this accretion disk forms promptly, and interestingly, it forms in the direction opposite to that of the star. So I don't know what observational consequences this can have, but this is something we find. It's basically because the gas with positive angular momentum is lost because it's unbound. So the disk forms from retrograde gas.
Sorry, Clément. Does that mean that if that disk is precessing, it's going to be retrograde?
Well, we don't know the stars.
Or not? Is that
He means retrograde with respect to the initial orbit, he's not talking about black hole spin at all.
No, that's independent on that.
You had some sort of feeding mechanism that was dependent on the spin, then you might expect that though.
I mean, generally it's going to be, I'm going to talk about a little bit of that, but I mean, yeah, if you have, the lore is that when you go to higher black hole spins, you're going to have a bias towards prograde orbits precisely because those are the ones that avoid, direct capture. But then if in the collisions themselves, you're turning the prograde gas retrograde, then it's going to kind of directly plunge into the horizon. And so this effect, I think, would lead to, a lot of direct gas directly plunging. Obviously, if you're continuously going from prograde to retrograde, you pass through zero along the way. And, even in the Newtonian picture, that stuff would fall right in. I think this would be this would have the effect of kind of very much shrinking the biggest black hole mass capable of producing an observable TDE, or at least producing accretion disk if that's a necessary condition for a TDE.
That's something that would be worth looking into.
Yeah.
Would it also just, in the cases where you can form a disk, they're just like imply that you're going to form a much more bound disk more quickly?
Yeah, you think a more compact disk. I mean,
Yeah.
If the disk ends up retrograde, it's sort of completely changed its angular momentum from the initial. So is the size of the disk at all related to RT, or is it something completely different?
So yeah, it turns out to be similar to RT, but as you said, this is not it's more of a coincidence. I think it's related to the sphericity of the outcome. I think if you were to have half of the gas on one direction, half of the gas in the opposite direction.
Yes.
But the takeaway is that I would have to understand why that is, because it seems like a coincidence. But the size of the disk is the total size is roughly 10 RT actually. But there's a spread in angular momentum, so it's not expected.
Yeah.
That you get exactly the angular momentum of the star.
Is it 10 RT?
Then RT, then that already.
That's big. I mean, you know, compared to the traditional circularization radius of 2 RT. Yeah. Well, how much mass in this is in the, so in the standard picture, you know, half of it is initially unbound and half is bound. And you're ejecting your prograde gas. I presume, what is your disk mass? How much has it gone down?
It's around 10% actually of the
What?
10% of the outflow mass, so it's quite small.
10%, the disk mass is 10% of the outflow mass.
Yes. So
Of the original outflow or the, so of the original stellar mass. So you mean,
so 10% of half of the
okay, so only 0.05 stellar masses is in your disk. Only 0.05, if it was a solar mass star, only 0.05 solar masses in your disk.
Let me ask you, what fraction of the initial mass, bound mass, actually participates in the collision? How much mass are you inputting in the domain of simulation?
5% of 10% of 2%.
No, it's you mean the mass that has been injected here
Yes.
throughout the simulation?
Yeah.
Yeah, I think it's roughly maybe 0.3 solar masses or something. So yeah, the simulation is not run from infinity, so we don't have exactly half a solar mass, it's slightly smaller than that.
And one question, we are accounting for angular momentum to try to figure out, you know, the probabilities of the result of this being retrograde. What do you think, you know, when you initialize this simulation with an outflow of mass? You know, there is a piece of stream that is still going around, which is no longer here, right? And that, you have a feeling for.
Yeah, so that's definitely one of the strong assumptions of that model, that we basically ignore the stream. It's supposed to be here. And at some point, this assumption should break down because the stream will become less and less massive, and the gas in the disk will become larger and larger. So there should be some mixing at some point, which is not clearly identified. So this picture will break up, will break down.
And how would you expect this to change if the collision was not head-on?
Oh, so in that case, the collision is not head-on actually.
Ah.
The simulation is done in the frame where the collision is head-on, but then there's a change of frame, and so the collision is actually the one you see here. That is between inclined stream.
I guess the question was, you asking, you know, what happens in vertical offset?
Yes,
okay.
sorry, yeah.
No, that's a very good question, and probably something that we can investigate with Ty. Yeah, in that case, I think what we found is that even in the most extreme case of a significant vertical offset, you know, the streams are collimated, the outflow are collimated in the direction of the streams, but still there's important spread in percentile. So the stream, you know, these kind of expanded streams, they would come back, but they would come back with a spread in percent that is significant, meaning that there would be, you know, some differential precession. So I think I would expect that even in this case of a strong offset, still the formation of the accretion disk would not be delayed by many more orbital periods. Maybe a few.
Okay.
Just back to this interesting point about the maximum mass. I mean, it seems like here, even if you had a non-spinning black hole, but very massive, you could have a star that is initially within the ISCO in terms of its orbit, but you end up with gas spread out to larger angular momentum. And so you could have an accretion disk, even if the very center of the star is significantly, you know, is inside ISCO.
Yes.
So that's an interesting wrinkle on what would events look like for non-spinning, but quite massive black holes.
So like 3 minutes left for the coffee.
Okay.
More questions?
Yeah, just
Or you
to
want to
finish
finish?
with the. So this is showing now the evolution of the radiation energy. Initially, there's no radiation, but you will see it will get produced by the same shocks that form the disk, and it will show up in yellow. So this is the radiation produced by the circularizing shocks, and it's not confined to this region because of diffusion. You know, these photons can actually diffuse and irradiate the large scale envelope. Interestingly, except in this cold spot here, that is screened from radiation, mostly because of its high density and the fact that it's moving in the opposite direction from the diffusing.
I have apologize. What exactly, I mean, the view, we're looking above. What is the?
Oh, it's a cut, sorry.
Oh, one of the, it's an edge on versus a.
Oh, no, this is the same thing, the same view, but here it's taking a cut through a large expanding.
One of the
sphere.
points is the stream collision radius, the other one is the
Okay.
level.
Oh, yeah, sorry, that's the self-crossing point and that's the black one.
And that's, and the one from the lower bit is the from above, looking at the black hole at the center, and the top bit is an edge on stream.
Sorry, this is exactly the same slice I'm considering in these two movies.
Okay.
And basically the stream came back, it crossed itself here, and that's the outflow from this collision, and that's the black hole. But it's a cut, so there's gas also in this, above this plane and below this plane.
It's a view from the top.
And is it at the same time?
Yeah, here it's roughly at the same time.
Sorry,
So-
yeah, I'm a bit confused too. Like, is the top, what is the top block? And then the left.
Here?
Yeah,
So yeah, here it's, you have to understand it as a region that is not irradiated. So there's radiation from these shocks that is diffusing out.
I think it's asking a simple question.
Yeah.
You know, that's the point where the two streams collided originally, and now in this simulation, that's taking us an initial.
So why does it linger? I mean, so you have this collision here, but now it wouldn't stuff go in all directions and ultimately, I mean, why did it linger in the picture? It's just like it seemed like from long after the stream had formed, you still had some kind of blob sitting around at the collision point.
Yeah, so this outflow is going on at all times.
Okay,
but even after the disk is formed, the outflow is happening.
Yeah, so the stream is coming back at all times.
but how,
So
even if the stream, certainly the stream from large radii is coming back at all times, but if, won't the inner bit just ultimately go away?
yeah, so that was really
This is the point
Martin's
I was
point.
making,
At some point, the stream will actually dissolve in the disk. That will happen, we know, at some point in time. But here we assume that it doesn't happen. So
Okay, so
outflow
this is, okay,
It's
so
fed from the
you're,
stream,
yeah.
But in principle, you could estimate, you know, when you should stop feeding.
Oh, yeah, I mean, it's like one period, it's gonna be actually much less than a fallback time. I mean, the time, so if you, in that picture there, essentially the collision is cutting off the bottom bit, you know, so by the time it takes that remaining bit to loop around and go through the point, after that it would end.
Well, you could just
Yeah.
calculate like, yeah, when the collision strength through the disk is like comparable to, or is significant enough to.
at the only time
stop
we do
it.
expect the stream to pierce through the stream,
Originally,
to
yeah.
pierce through the disk because it's much more dense.
Yeah,
Later on, the stream will become less dense, the disk may become more dense, and so that will, some mixing will happen. And this picture, having the outflow continuously launched, will break that.
yeah.
And I just give the last slide. So this is, yeah, just the main conclusion is that we see we can obtain the bolometric luminosity from the simulation, and we find that it's reaching up to a few 10 to 44 arc per second. That's the black line. And that's encouraging because it accounts for observed values. And using this first principle simulation, we can also propose a mechanism for optical emission strongly based on the processing layer model. Basically, the disk will emit in extreme UV and will interact with the large scale surrounding envelope being reprocessed into optical emission. And we think that the presence of this screened region around the self-crossing point may be important in this process because of enhanced bound-free opacities. So yeah, that's it. So this is, I hope that this work really based on first principle simulations can be the way forward to have a robust paradigm for our TDEs that can be used to exploit the thousands of observations that we expect in the future.
Okay, I'm wondering whether we should have one or two presentations.
Oh yeah, otherwise it's fine with other questions.
Are there a couple of questions?
I think it's fine. If you start.
Just a quick one. So I mean, in terms of fueling the disk, it's not at all like the just an isolated disk type picture where it's just material falling in within like the same plane as the disk. It's all coming in from different angles. Right?
Yeah. So this sphere is a 3D sphere.
Yeah.
So this kind of obtains naturally the cooling envelope that Brian was talking about, in the sense that there's a large scale envelope, and inside of it, all these interactions, the disk forming.
Right.
I was going to quickly ask, do you envision the property of this envelope to be similar to what Brian has in mind?
Yeah, definitely.
I was gonna just, so in the standard kind of picture, you have the stream that's coming in with the angular, certain amount of angular momentum, and then it in principle could circularize at the circularization radius, which is twice the tidal radius. That's just from conservation of angular momentum. You're losing energy and you're conserving angular momentum. And you're now having your stream collision, you have this prograde ejected stuff, this retrograde disk, and you said that the radius of the retrograde disk is 10 RT? Is that what you said?
Yes.
I mean, there's
So most of outer radius is 10 RT, but most
yeah,
of
yeah. So the outer radius, but I mean, that's kind of, obviously you don't have enough angular momentum to circularize at 10 RT. So you're really going to have, if you defined a kind of mean radius, it'd be much. I guess I don't know much angular momentum is
redistribution of angular momentum.
Yeah, it's being reduced. Yeah, so you have
angular momentum is actually in the direction of the star, but this gas is unbound. And the angular momentum of this unbound gas is larger than that of the star.
Yeah. So you have some,
want to have
but the magnitude of your residual disk is probably, well, I mean, it's interesting. I mean, it's going to be small. I mean, even if the edge goes out to 10 RT, maybe, I mean, it'd be very interesting to see what is the angular momentum of that disk.
Basically, what the self-crossing shock does is that initially the angular momentum distribution is centered on that of the star, very narrow distribution. And what the self-crossing shock does is to spread this distribution such that you have now higher angular momentum. This one is mostly unbound, but also lower angular momentum. And this is the lower angular momentum gas with value in absolute value larger than that in the star that forms this. So that's why you can afford to have.
But do you think, I mean, it probably spreads it by an amount that's not all that different from the initial angular momentum, just because I'm not sure, but one can work that out, I think, from your picture of the average velocity ends up being the same as the incoming velocity, but it's in a random direction.
Yeah, it can't make it that much bigger than the, I agree with you.
There seems to be several topics of conversation during coffee, so we should thank them all again.